Okay, active versus passive rift margins. Let's first start by defining what a rift margin is. A rifted margin, or one definition of a rifted margin, is the transition between stretched continental lithosphere and new oceanic crust formed during continental breakup. Now, this is by no means a fully encompassing definition. It's rather simplistic, but I think it fits the scope of this video pretty well. And just to touch on two terms there that you may or may not completely understand, they mention both lithosphere and crust, and there is a distinct difference between these two. The lithosphere includes both the crust and the uppermost portion of the mantle. Okay, in the crust you will experience brittle deformation, and in the uppermost portion of the mantle you will experience ductile deformation or plastic deformation. So when we say lithosphere, we're considering both of these things together. When we say crust, we're talking about just that uppermost portion that experiences only brittle deformation. Okay? If we want to define a rifted margin a little bit further, we can say that rifted margins form when the lithosphere is pulled apart, creating fault-bounded basins in the crust, thinning the lithosphere, and eventually initiating seafloor spreading. Now, there's an important distinction to be made here as well. Seafloor spreading is the terminal point or terminal state for many rifted margins, but not all rifted margins. And in fact, there are plenty of examples here on Earth where we have rifted margins that do not show signs of seafloor spreading. So not all rifted margins are seafloor spreading centers, and seafloor spreading centers are distinctly characteristic of plate tectonics here on Earth. We don't see seafloor spreading centers taking place on other planetary bodies as of yet. Okay, active rift margins. So we'll touch on three aspects for both processes, and that'll be driver, sequence, and magmatism, as I think these are most important to distinguish one from the other in basic terms. So the driver of an active rift margin is a mantle plume or focus mantle upwelling, which heats and weakens the lithosphere from below. The sequence of this will result in regional doming and uplift, followed by large volume magmatism, such as flood basalts, and finally localized extension and breakup. The magmatism is described as magma-rich, volcanic margins with thick igneous crust, underplating, and seaward dipping reflectors. Don't worry too much about those last 2 points, underplating and seaward dipping reflectors. Those refer to geophysical analyses that we won't dive into too much in this video. But nonetheless, if we look at this figure down here at the bottom, you'll see that the mantle plume is rising up through the asthenosphere. It is heating that mantle lithosphere from below, causing ductile extension at the bottom of the lithosphere, which then translates to brittle extension in the crust, creating those fault-bounded basins we were just talking about a moment ago. Okay, so what happens in passive rift margins then? The driver for these are going to largely be far-field plate forces. So these are tectonic forces happening elsewhere along the plate. If you imagine a lithospheric plate being pulled apart at some point, a weak point in the plate perhaps, and if we're not talking about a mantle plume coming up and heating and driving that splitting, then there must be something potentially pulling on the plate from another direction, causing that extension. And that's exactly what they're talking about here with far-field plate forces, such as slab pull, ridge push, or collision elsewhere. These stretch the lithosphere, and the mantle responds passively to this extension. Okay? The sequence would look something like a fault-bounded rift basin and subsidence first instead of the domal uplift that we saw with active rift margins. In a passive rift margin, we'll see that subsidence actually takes place first. The asthenosphere upwells as the lithosphere thins, and decompression melting may occur later. All right, so the key point really is that upwelling is a consequence of the lithospheric extension rather than a driver. This results in typically modest magmatism, often delayed. Many passive margins are considered magma poor and often lack flood basalts. All right, so let's look at some examples of these. One of Perhaps the most famous examples on Earth of an active rift margin is the Afar Triple Junction. This is in the Eastern African rift system, and a triple junction is where three fault systems meet together to form a junction. In this case, it's what we would consider an RRR triple junction, which stands for rift, 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 right? So the Red Sea and the Gulf of Aden are two rifts, and then the Ethiopian rift is the third one. We have strong evidence for mantle upwelling associated with Oligocene basalts here and ongoing magmatic rifting. Okay, so we have a bunch of flood basalts going on there, which is a key piece of evidence that this is an active, not a passive rift, right? And in case you're wondering what the sequence of rifting looks like here, the Red Sea and Gulf of Aden rifts began forming around 35 to 23 million years ago, while the main Ethiopian rift began to form more than 11 million years ago. Okay, so the Ethiopian rift is the youngest of the three, while the Red Sea and Gulf of Aden are older, and that can actually be somewhat you can somewhat pick that apart yourself just by looking at this image here and seeing that the Gulf of Aden and the Red Sea have begun to form actually narrow seas there. So they've spread apart enough to form narrow seas, while the Ethiopian rift has not reached that point yet, so it's younger. And so just kind of touching on that evidence of how we know it's an active rift, analysis of over 130 volcanic samples from the Afar region shows a repeated chemical composition, which suggests the magma is originating from a single shared upwelling rather than separate sources. So not only do we know it's an active rift, but we're also able to determine through chemistry composition of the rocks there that these are all coming from a single magma source. So it's pretty neat geologic environment where we have this one massive mantle plume causing a triple junction in that region. Pretty cool stuff. Let's then look at an environment here on Earth where passive rifting is occurring. Again, perhaps the most famous example of this is the Iberia-Newfoundland conjugate margins in the North Atlantic. This is a magma pore margin that exhibits a lack of significant volcanism, exhumed continental mantle, and a wide, complex continent-ocean transition zone. And we'll touch on those here in just a moment, kind of give you some ideas. So this figure up here on the right is the Newfoundland Iberian plates kind of splitting apart. So this represents around 120 million years ago. And for those of you who don't know what the Iberian plate would be, or kind of like where to place that in your head, it refers to essentially the Iberian Peninsula, which is today Spain and Portugal. Okay. And then Newfoundland. That they were together at one point, and then they split apart during the breakup of Pangaea. Okay. And we're able to determine this is a passive rift not only by the lack of basalts we see, but also by the large-scale detachment faults that slice through the crust and upper mantle, exposing mantle rocks along the seafloor over wide areas. I have another figure up here showing you what a detachment fault looks like, and this is essentially where you have a bunch of half-gravens, so think sort of similar to a normal fault basin, but there's been so much extension there that they've actually separated from the underlying bedrock below, if you will, or the lowermost part of the crust, and are now faulting along that bottom portion as well. And this is a very characteristic. This is very characteristic of passive margins. Okay, and then we also see the continent-ocean transition zone, which is different parts of the margin were affected at different times and with different faulting styles. The presence of multiple detachments with recurring dip reversals, which control the geometry of exhumed mantle highs and ridges. So just to wrap things up here, we talked about drivers and active and passive. And active, it's plume or upwelling driven. Mantle initiates the rift. And passive, it's plate driven. So these are far field stretches that initiate the extension. Typical examples would be the Afar Triple Junction for active, the Iberia-Newfoundland margins for passive. Magmatism, you're going to have a lot of magmatism with active, not a lot with passive. And then the first observable effects, which are also pretty important. With active, you're going to see that domal uplift occurring due to the magma upwelling, followed by large volume volcanism. And in passive, you'll see more normal faulting and subsidence in the rift basins. Volcanism mainly occurring later due to decompression melting. Okay, I think that pretty much wraps everything up. Thank you guys for watching. I hope this kind of gives you a better idea of what the difference between these two processes are. I did this really quick. This was unscripted, so hopefully it's received well, and I will catch you guys later. Peace.